All right, so I am very excited about this lesson because we're finally going to get a chance to define the beginnings of calculus, at least. We're going to get to set a little bit of expectation about what the power of calculus is and why it was important for mathematicians to develop it. So, I want you to take a look with me at this graph. This is a beautiful graph of the function y equals x squared, which I think we could agree to refer to it as a curve, right? As opposed to, say, a line like y equals x or y equals 2x, y equals 10x plus 3. This is a curved graph, a curved function. So what I want us to think back to is in Algebra 1, actually, even. This is pretty elementary algebra as far as things that we learned very early on in algebra, is we learned how to take a line, some kind of straight graph of a straight function, and we were able to figure out what the slope or what the rate of change of that function was, so how quickly that function was changing. And we did it by finding 2 points in the line, and then we used the slope formula, which is the change in y over the change in x, or the rise over run. We'd take like 2 y values, 2 x values, and we'd subtract them and figure out what that rate of change was. And that was pretty straightforward, and probably, I'm thinking at this point, pretty intuitive. Like, we can understand why taking the change in y over the change of x would help us to understand how quickly something is changing. However, you may have noticed we never tried to find the rate of change of a curved graph. So something like, we'll go back to this graph of y equals x squared. If I were to ask you to find the slope of the line, you wouldn't be able to answer, because at least right off the bat you should think, well, there is no one slope for this graph. In fact, if we look, because if slope is rate of change or how quickly something is changing, if we look down, say, at the bottom of this graph, right down here, oops, I need my nice drawing color here. Down at the bottom, the rate of change is 0. It's kind of like stopped. But then if I move up, I find that the graph is changing faster and faster and faster and faster. In the reverse direction, it's also changing faster and faster, except in a negative way. The slope is getting more and more negative, whereas here the slope is getting more and more positive. It's increasing faster and faster and faster. So for me to ask the question, what is the slope of this graph, of this function, you would not be able to answer that question. Now, it might seem more reasonable if I were to say, well, what is the slope of this graph at this point, at A? And to give you something to compare it to, it would be kind of like if I took an object and I threw it up in the air, and if you've ever seen anything about projectile motion, there's like a little guy here. I'm going to draw a little picture. And he throws something up in the air, and it goes up, up, arcs up to the top, and comes back down and hits the ground, well, somewhere off the page. So it has this nice curved, I feel like I need to like hide under my picture. It has this nice curved shape that looks a lot like a parabola. Well, if I wanted to find how quickly that object was moving, or what the slope of it was at any point in time, I would need to look at a specific point along the way. Let's say if I wanted to know its speed, I'd probably need a radar gun to look at each little point along the way. But in mathematics, there's got to be something better than a radar gun trying to figure out how fast I'm throwing this ball across my math screen here. Is there a way, and it seems like there should be, right? If you think about it, there should be a way for us to find out information about each precise point along a curve, because that information is important. We really don't want to be satisfied with the idea that we have to say, here, I'll draw this again. Here's our curve. We don't really want to be satisfied to say, oh, well, I don't know the exact slope here, but I could find a point kind of close, and, we could average it. We could figure out what that is. That doesn't seem right. If you like mathematics at all, which I hope if you've gotten as far as calculus, you like something about mathematics, that should bother you. That's not okay. That's not precise enough. And so that's what we're going to talk about. Is that possible? And if so, how? So let's go back to our graph here. All right, we have, erase my little mark there. We have this point A, and in order to find the slope, right now the best way we know to do that is to try to create a line that approximates that location, which I know I just said we don't really want to do, but that's the closest we can get to an answer. So maybe I take the point A and I take some point up here on the line, and if I were to drop that point, I get a nice straight line. Now, I could find the slope of that line, and I could compare it and say it's approximately the slope. But I don't think that's a very good line. In fact, I think I could make it better if I were to maybe, let's make another line. Let's say I went here and I made it a little closer, like right there. So let's hide our first line because I don't like it that much, and B. And I think this line looks a little bit better. It's a better approximation, but I think we could do even better than that, because I think we could take, let's forget this one and this one. Let's see if I can make a line that's really super, super close, like maybe right there. So now I have a line that actually is getting to a point where if I were to find the, let me remove this for a second. If I were to find the slope of the line you can see there, it would have a slope very, very similar to the point A, right here. Let me put the line on. I think it would be very similar. Not exact, but very similar. And in fact, if I could do better, and instead of getting that line to be, say, I don't know, 0.5 of a distance away, or maybe a quarter of a point away, or I can make it just 0.1 away. The closer I make those 2 points to each other, the more exact my estimate, my guess would be. But if I could go so far as to take those 2 points and bring them infinitely close together, in fact, so close that they basically become the same point. So I'm basically finding the slope of 2 points that are getting closer and closer together and are essentially the same point. I could finally get to the point. If I could find, let's say, the limit as I approach them becoming exact points, I could actually find the exact slope at that exact point. And that is what we're going to try to do. Let's see if we can write that out mathematically and see if it's possible. Can we solve this using the idea of limits to bring it not from far to close to closer to, pretty good, but to actually bring it in infinitely close to make it essentially exact using the concept of limits. Okay, here, let's go to this blank slide here. In a normal rate of change problem, we'd have our, I have blue right now. Let's do red. Okay, so we'd have a change in y over change in x, right? That's how we would typically solve a problem like this. And what that means is that we would take, y2 minus y1 over x2 minus x1, and we'd get a solution. So let's try to rewrite this to be 2 points that are very close together. In fact, I'm going to call the initial point my x1, y1. So normally we have x1, y1 is our first point, and we have x2, y2 as our second point. So I'm going to rewrite this. I'm going to use a different color so that we can compare. And I'm going to say, let's turn this into the point. We'll say A and f of A. So that would be the original point. Actually, on our parabola, if you want to look at it, that would be the point 2, 4, right? 2, 4. That would be our original. Right now, I'll just call it A, f of A. And then we want a point that's really close to that. So we'll call it, I'm totally going to run out of room here. Let's see, I'm going to put it underneath. That's going to bug somebody. Here, let's erase and start over, because I know this is going to drive somebody absolutely crazy. Let's erase, and let's try this again. All right, so we said our point was a and f of a. A, whoa, what did I do? I changed it. This is why you don't change your ideas mid-video. Okay, a, f of a. And the point that's really, really close to it is going to be, we'll call it a plus h. So something really, really close to a, but we have to have some difference, right, in order to find the slope. So a plus h. And then the y value would be f of a plus h, right? So those would be the 2 points. Now, if I were to write that into a formula, what I'd have to do is I'd have to put y1 would be f of a, y2 would be f of a plus h, x1 is going to be a, and x2 is going to be a plus h. And I'm going to have to do it out. So that would be, let's do f of a plus h minus f of a all over a plus h minus a. Okay, so that is the formula for finding the average rate of change between two very, very close points. But if I want them to be better than close, if I want them to be infinitely close, I'm going to have to take this expression that I've created, and I need to turn it into essentially a limit as the distance is going to 0. So let me clear this away here for a second. We're saying this is f of a plus h minus f of a all over a plus h minus a, which, by the way, if I have a plus h minus a, those a's are going to cancel and I'm really just going to have a. So why don't we just, for good measure, since I've already written this a couple times, why don't we just call this h, just to make it simpler? Why be redundant? Okay, so we want to find the solution to this equation when h is the distance, right? H is the distance between the first point and the second point. We want to bring that not to 0.5, not to 0.1, not to 0.0001. We want to make it essentially 0. Of course, we can't make it literally 0, but we could find the limit as h goes towards 0. That we could figure out. So this is how we would write it. If we can find the limit as h becomes essentially nothing, the distance between these points becomes essentially nothing, then if I can plug in values for this formula, which is basically change in y over change in x, which we simplified, I can find not just the average rate of change, not even a good estimate, but I can find the exact instantaneous rate of change or instantaneous slope of any function at any point along that function, as long as it exists, right? I mean, like, you can't find slope on a point that doesn't exist, and we'll talk about that later. But if it exists, if it's like a typical nice continuous function, I can find the instantaneous slope anywhere on that function. And I don't know if that seems kind of like boring right now while I'm just talking about it on the video, but that is an incredibly, incredibly powerful piece of mathematics right there, because it allows us to look at things that are not consistent and be able to understand exactly what's going on at each infinitesimally specific or infinitesimally small point in time. That is something that really requires an example to kind of flesh out beyond what I've just described for you. So I do want to make sure, let me give this back to you for a second. Make sure you write down this formula. You should actually have the whole kind of proof out there somewhere. But this is the important part underneath, right under there. Limit as h goes to 0 of f of a plus h, which is y2, minus f of a, which is y1, all over h. That is your formula for finding instantaneous slope. And if you want to write that down, just write instantaneous slope, formula for instantaneous slope. And in the next topic video, I'm actually going to do a problem out that requires us to use that formula, and we'll see how it works. Now here's the one last little tidbit that I want to tell you. That is, instantaneous slope is a derivative. Or I should say, also, a derivative is instantaneous slope. So half of what we do in this year, from now until, say, Christmas time, after limits, we are going to be talking about derivatives, which means we are going to be talking about how to find instantaneous slope. The way we do it right now with limits is really, really important. But I'm going to just kind of throw it out there that in Unit 2, we're going to find out how to do them so fast that the majority of instantaneous slopes you're going to be able to find like this in your head without maybe even writing anything down. So we have a long way to go before we can do calculus really efficiently, but you are now beginning to do real, true calculus in the work that you're going to be working on for Lesson 4. Okay, that's it for Topic 1, and I will see you in Topic 2 with an example.